Hi everybody, and welcome to Math 252, Calculus 2. My name is Blake Winter, and I will be your professor this semester. I'm a pretty informal person, as you might be able to see, so I'm perfectly happy to have my students call me by my first name, Blake, but if you prefer and are more comfortable with it, you can certainly call me Professor Winter, you can call me Dr. Winter, whatever makes you feel comfortable, really. If you need to get a hold of me during this semester, the easiest way to do that is via email. And this is, of course, in your syllabus, which we'll go through here in a moment. But I figured I'd throw it up on the board for you, bkw42@medaille.edu. For those of you who are physically present on campus this semester, if you want to come see me in person, my office is in the Huber building, and I'm in 122. So I'm down on the first floor. It's not like I'm a little way down the hall from the library, if you know where that is, and across from our remote learning and tech people across the hall, basically. So, yeah, Huber is not a huge building, as you're probably aware if you've been on campus before. So if you come through the first floor and you just look through the whole thing, there's really just one hallway that goes everywhere, and eventually you will find me. My office hours, I believe, I will let you know if this changes, but my plan at this point is Monday, Wednesdays, 12:30 to 1:30, Tuesday, Thursday, 2:55 to 3:55, and I do plan to be logged into a Blackboard Collaborate session or something so that people can come to office hours virtually and ask me questions that way, since this is a remote course and everything, and some students are going to be off campus for a bunch of time. So yeah, we'll see how all of that goes, but I will try to be in a Blackboard Collaborate during those times. All right, so let's take a look through the syllabus. Now you can access the syllabus on the Blackboard website, and I believe everything is all set with it, but I figured we'd run through it here. So the textbook that we're going to be using is Stewart's Calculus Early Transcendentals 8th edition. It's very important that you get the Early Transcendentals because they've also got Stewart's Calculus, just no extra title there, and that is unfortunately not the correct book. It needs to be the one with the Early Transcendentals. And you may want to have a calculator, although personally, I always put in there that people should want to get a calculator. You might want a calculator, but the truth is I make everything so that you shouldn't really need a calculator for almost any problems that you have to do this semester. Let's just quickly go through the sort of boilerplate announcements that are in probably all of your syllabi this semester. If you have any sort of accessibility needs, you should contact the Accessibility Services Department, and there's instructions in there for doing that. We can, of course, accommodate pretty much whatever you need, but for legal reasons, you do need to actually let them know, and they need to have official, yes, you get this certification or this accessibility thing, just so that we don't have confusion with everybody as in terms of who's supposed to be getting what. So there's information in there about how you can email them or go see them. They're actually down the hall from me in Huber, so if you need to talk to them. Academic integrity, don't cheat. I trust that at this point you should already know kind of what constitutes cheating, and don't do it. And if I do catch you cheating, then you will fail that assignment, and if it seems like it's a severe enough infraction, then I may get escalated for further discipline from the college beyond just me failing your assignment there. Title IX, if you have any concerns about discrimination, harassment, or any other kind of problems really, then please don't hesitate to contact the Title IX department here. That will help you to address that. So there's information about how you can talk to the Title IX coordinator there, phone, email. You can even go see them in person if you need to, and they'll be happy to help you out. Campus emergency closure. Since this is an online course, that doesn't really affect us too much, but if for some reason there's something that has been thrown off in terms of what's going on, I will let you guys know. I will send you an announcement over Blackboard and let you know what to do. About this course, this is Calculus 2, so it is the second course in the sequence on calculus. And if you want to see all of the different official objectives in there, I will let you guys take a look through the syllabus and figure that out on your own. Evaluating. So how do you get your final grade? This is something that everybody always wants to know. The way that I do this is you're going to have 3 different kinds of assignments here this semester. You're going to have 3 tests throughout the semester. You're going to have homeworks, which in the syllabus, that's just lumped in under quizzes and assignments. And I do that because depending upon how I format the course, sometimes I do some quizzes, sometimes things get mixed up. Because we're doing this as an online course like this, I think we're going to stick with just doing homeworks for that section, but I'm leaving things open just in case I decide that I want to make a little change here and there. Then we will have a cumulative final exam. So the final exam is weighted at 30%, tests are 40%, and your homework, quizzes, and other assignments will be 30% of your grade. I take your final percentage, I subtract 57 from it, and I multiply it by 1/10, and then I round that to the nearest GPA score. And the reason I do it this way is because I want it to be a linear function from your percentage to your GPA. The way that most professors do things is a grade of a B will have a span of like 4 or 5 percentage points, but a B plus will only be about 2 percentage points. And the problem with that is going from a B to a B plus is the same GPA as a B plus to an A minus. Well, I want to make sure that your GPA reflects your actual performance in the course in a linear way. So if I am changing your GPA by 1/3, which is what happens when I go from a B to a B plus or a B plus to an A minus, that should reflect the same change in percent in your performance, no matter where you are at. So you guys are Calculus 2 students. Hopefully you're familiar with linear functions. If not, you'll probably want to review linear functions pretty quickly here. But that is why I use this formula. And it might seem a little bit complicated, but the truth is it's not really that complicated. And what it works out to be in practice is 96 or so is an A, 86 is approximately a B, and then so on and so forth, roughly every 10 points there. Now, how are you going to do these assignments? Well, everything in this course is supposed to be online, so we're going to be using WebAssign through Cengage, and I posted the information that you need to be able to get into our specific course on the Blackboard thing. So if you go into the thing about Cengage WebAssign, that gives you the information that you need to give them. You also do need to buy an access code, which should hopefully come with your textbook. I hope that the bookstore has got everything worked out that way. If you don't buy it through our bookstore, make sure that you are getting the correct edition of the correct textbook and that it comes with the web access code. I always feel kind of bad about doing this because I would like it if you guys could buy used textbooks. Unfortunately, we're having to rely upon online homework and testing systems here this semester, so I do need to ask you guys to buy the online access code. And yeah, that kind of throws off being able to buy used editions, but that's where we're at with everything happening right now. In terms of attendance, so this is an online course, but I do expect you to watch all of the lectures that I record for you, and I also expect you guys to keep in touch with me in a timely manner. You know, let me know how you're doing, do your homeworks in a timely manner and things like that. If you stop doing stuff, I'm going to wonder what's going on. I don't specifically count attendance towards your grade, but there it is. I do want to make sure that I kind of have a feel for how you guys are doing at any given time. And on that note, in terms of deadlines, so normally the homeworks are going to be due on Tuesdays, but that may shift. I will try to keep you guys up to date, but you can always just go in. The best thing to do, go in and check on Cengage and see when is the homework due. Because I may sometimes push off the deadline if I feel like, oh, you guys should have a couple extra days to work on this. I did Tuesday just because Madai has this thing about Tuesdays and online courses and things being due on Tuesday. So that is our official, usual due date for stuff. But I may decide, hey, you guys need a couple extra days for this or whatever. Say, yeah, this week it's going to be pushed off to Thursday. But if you specifically need some kind of an extension, you know, I want to be flexible. I know this semester's crazy for everybody with whatever's going on, and this is our first time trying this as an online course. So I'm going to be as flexible as I feel like is fair to everybody, but I also do want to have deadlines here so that everybody is practicing the material every single week. I don't want somebody to say, I'm just going to put everything off for several weeks and then try to catch up. That's really not a good idea, honestly, especially in Calc 2. I will tell you, Calc 2, it's not an easy course. This is going to cover some fairly tricky material here. So, Calc 1 is an easier course than Calc 2, by far, in my opinion. A lot of students, I think, agree with me, and certainly my experience as a student was that Calc 2 was a step up in difficulty. Now, hopefully we will find ways to make everything make sense to you, and you won't find that it's too bad. I don't want to make you guys feel like, this is going to be terrible. It's not, I hope, but it is going to be a course that requires a lot of hard work, honestly. I don't want to sugarcoat things either, okay? So I will do my best to make sure that everything makes sense, and I'm happy to always give you guys extra help, extra answering questions and things like that, but I want you guys to be prepared. You will need to spend some time studying this. It's definitely not a course that you're going to probably just skate through unless you happen to be really, really, really talented at this stuff or something. And if you do have some reason like, I can't take the test when I have scheduled that test, if you say that you've got something going on, that's generally fine, but do try to let me know ahead of time. If you have an emergency, like I was going to take the test and something horrible happened. I had a student last semester who had her house catch on fire, for example. Just let me know. I mean, again, I'm going to accommodate as much as I can, but I do need to know what's going on as soon as possible so that we can get to that. I believe that covers just about everything in the syllabus. Now, I do want to say one other thing about attendance and watching the lectures. So you should expect throughout this semester to spend about 3 hours a week watching the lectures. That's about how much time we would spend if this were an in-person class. We would have 3 hours a week of lecture time. That doesn't necessarily mean I'm going to literally upload 180 minutes of lecture every week, though. Because here's the thing. When you are watching these lectures, I will often have points in the lecture where I'll show you some examples, but then I'll give you examples and say, okay, I want you, before you watch how I do these examples, I want you to take a minute and see if you can figure them out on your own. So I expect you to do things like pause the video for 10 or 15 minutes and work through a couple of problems, and then restart the video and watch to see if you can follow, did you do what I end up doing? Or did you get the right answer? Did you understand what's going on? And I think this is important. This is something that I do when I'm doing in-person lectures as well. I will pause lecturing and say, I want you guys to take a few minutes and work on these problems so that you can get a feel for what's going on. Mathematics is not a spectator sport. If you've taken any classes with me before, you've probably heard me say that. But it's true, okay? You do not learn math by just watching me do math. You have to do the math yourself. You can watch me and it can feel like everything is making a lot of sense to you, and then you go to do your own problems and you realize, actually, I'm not really sure what I'm doing. I feel very lost. The point of having you stop in the middle of that kind of thing is to kind of help you cement that into your head to make sure that you are understanding it, and so that if you're not understanding it, you can immediately go back and rewatch the examples that I've done and kind of hopefully clear up what's going on. Or you can send me a question and say, hey, I'm in the middle of this lecture and I feel like I'm very lost about this. And of course, I will tell you how to do those examples afterwards, but I do want you to, when I say pause the video and work on these, I expect you to actually do that and spend some time doing that. And that's kind of part of watching the video. The other thing is that since these are videos that we're not, you're not watching live, I expect you guys, if something doesn't seem to make sense, rewind a few minutes, rewatch it, and kind of, take some time that way. So the point is, if I upload, say, a 30-minute video, it might take you 45 minutes, it might take you an hour to actually watch that video. And if we were doing in-class stuff, right, that would be normal, because I'm not spending every moment just up there talking. I'm spending some time having you guys work problems. I'm spending some time answering your questions. So yeah, in terms of what are the videos going to be like, expect to spend at least 3 hours watching them, but that doesn't necessarily mean there's going to literally be 180 minutes, which is 3 hours, of video uploaded every week. If I uploaded that much, then it would take you like 4, maybe 5 hours to get through the videos. So that's kind of why We're not going to literally be doing videos in 60-minute chunks or something like that 3 times a week. All right, so on that note, let's start off with a little bit of review. So for this first week, I kind of want to review the stuff that is in chapter 5 of your textbook. And this is the stuff about Riemannian integration and the fundamental theorem. I do apologize for this incredibly tiny whiteboard. This is the only thing that I found in my office that I could use. I hope you guys can see this okay. I also hope to have a slightly larger whiteboard at some point that I can use. But this is what we're stuck with for the moment. So, I want to remind you about Riemannian integration, and I also want to remind you about the fundamental theorem. Hopefully, this was something you covered in Calculus 1. In our Calculus 1, this is the stuff that we end the semester with, and then you kind of jump back into it in Calculus 2. But I figure it's good to refresh your memory on this stuff and make sure that everybody is kind of on the same page here. So the idea behind Riemannian integration, it's actually an idea that goes back far, far before Riemann, but he kind of put all of this onto a rigorous footing, okay? So these ideas had been explored extensively, but Riemann, Bernhard Riemann, very famous mathematician who did a lot of really cool stuff, he was the one who sort of put all of this into onto a rigorous foundation. And what was his idea? Well, his idea, and again, it's not so much his idea, other people had been working with this stuff before then, but the basic idea is, what would happen if I wanted to find the area of something? Like, let's say that I just have some random shape and I want to find the area of it. Well, the idea that he uses is, let's try to approximate this thing. See, we know how to find the area of a rectangle. A rectangle's area is base times width. But this is not a rectangle. In fact, this doesn't even have straight lines as its boundaries. However, what we can do is we can try to fill this thing in with rectangles. So the idea is you cover this thing as best you can in a bunch of rectangles. Now, there are problems with trying to do this. The problems really come down to the fact that depending upon how you choose to build these rectangles, there's a lot of different choices involved. And depending upon those choices, well, different things could happen. But the idea is we can approximate the area using these rectangles. And if we want to approximate this area, even better, what we can do is we can say, okay, well, let's use more rectangles, which one way of doing more rectangles is to make the rectangles skinnier. So these are some fairly wide rectangles, but if I use skinnier rectangles and use more of them, I'm not going to draw it because it would take me forever to draw, but I would get a better approximation. Because the problem, what I'm missing here, is I'm missing these little pieces here, and depending, like here I've chosen a rectangle that has a little extra, but it's missing a bit there. Well, hopefully, if I use smaller and smaller rectangles, the stuff that I miss and the extra stuff that I pick up is going to get smaller and smaller. Now, of course, Riemannian integration is not just concerned with areas. That's just sort of the motivation here. So the idea behind Riemannian integration is, if I have some function in the plane, I have a point A and a point B, and let's say that this is my function y equals f of x graphed here, and I want to know the area of that region minus the area of this region down here. So let's call this A1 and this A2. And how would I be able to find A1 minus A2? Why would I want to find that? Well, that's another question, and we'll get to that in a moment. But here is one reason why I might want to find that. The area that is above the axis but below the curve minus the area below the axis and above the curve. One reason you might want to find that, and we'll come back to this picture in a moment. Really wish I had a second whiteboard here so that I could do this a bit better. But one reason you might want to do that is because if we were talking about a situation where the function is piecewise constant, well then this would have a very simple interpretation. Like let's say, actually, instead of x, let's say that this is the t-axis and this is the velocity axis. In other words, this tells me velocity as a function of time. Well, if this is constant on different intervals, then the total change in position is going to be the area under the velocity curve but above the axis minus the area below the axis but above the curve. So this A1 and this A2, A1 minus A2 is the total change in position. So this is one reason why we want to have this subtract the areas that are on the upper half, or subtract the areas, add the areas that are on the upper half, subtract the areas on the lower half. That's kind of the motivation for why you want to do this sort of thing. So Riemann's idea is that we can do this for an arbitrary function in the following way. We use that rectangle idea for finding areas. And if I have, here's my a and my b, here's my function again, y equals f of x, what I'm going to do is I'm going to break up this interval into pieces, and I'm going to put a bunch of rectangles here. And then what I'm going to do is I'm going to calculate the areas of these rectangles, add the ones where the height of the rectangle brings them up here, and subtract the ones that are upside down in the bottom half of the plane. And then ask what happens as we take the limit as the width of these rectangles gets smaller and smaller and goes to 0. So what we're going to do is we set up a Riemann sum which looks like the following. We sum from I equals 1 up to n f of xi star times b minus a divided by n. And what does all of this mean? Well, b minus a. B and a are the endpoints. B is the right-hand endpoint, a is the left-hand endpoint. Well, I shouldn't necessarily say that because occasionally we actually flip this around. But b is the endpoint, a is the starting point of what we're looking at. N is the number of rectangles that I cut this thing up into. And xi star is a point in the ith rectangle's base. In other words, the height of the rectangle is taken by evaluating the function at some point inside of the base of the rectangle, and that's it. We don't really have to worry about anything else there. Of course, the problems here are numerous. First of all, there's a different set of Riemann sums for every value of n. Secondly, for any given value of n, there's an infinite number of choices for these x of I star points. And it's kind of nice to see this graphically, I think. If we go back to that picture that we had a minute ago, where I said, here's my y equals f of x, if I want to take, say, just for the first rectangle, I can take x1 star to be here, and then the height of the rectangle would be this. But I could also take x1 star to be maybe the right-hand endpoint, in which case the rectangle would be a little bit shorter. I could take it to be the left endpoint, in which case the rectangle would be a little bit taller. There's a lot of different choices here for what are the values of the rectangle that we can take. And similarly, if I take some other section, like let's say I have, here's 2, here's 3, so x3 star would be somewhere in here, but where exactly? Well, depending upon where I choose it, I can get many different heights of rectangles here. Anything going from this small rectangle, sorry, that shouldn't look like part of the rectangle, that's just where we can pick the point. Anything from this small rectangle up to this taller rectangle is acceptable. So there's lots of different choices. And how do we sort of make sense of that? Well, the point is actually that there's just many Riemann sums that are possible, and that's fine. Because we don't actually, in the end, care about any specific Riemann sum. What we do care about is what happens as we take the limit as n goes to infinity. And this corresponds to taking the width of the rectangles and making it skinnier and skinnier. So we define the definite integral from a up to b of f of x dx. This is equal to the limit as n goes to infinity, sum from I equals 1 up to n, f of xi star times b minus a over n, provided that this limit exists and does not depend upon any of the choices involved. Now, that's an important caveat. It cannot depend upon the choices involved. So it might be the case that you could take the limit of the Riemann sums, but in order to make the limit well defined, you might have to make specific choices for your xi stars. That would be no good. We want to make sure that this limit does not depend upon how I mess around with these things. Here's the good news. In a lot of situations, you can actually show this limit will not depend upon the choices of the xi stars. And the reason for that is because essentially what you want to do is you want to be able to see that there's sort of a smallest possible Riemann sum and a largest possible Riemann sum. Okay, and so is it easy to see that in all cases? Well, the answer is actually kind of, yeah. In some cases, it is easy to see that there's one specific sum that's going to be the smallest and one that's going to be the largest. How? Well, to give you the simplest possible case where this is true, let's suppose that f of x is increasing on the interval from a to b. In that case, the smallest Riemann sum is going to come from taking my x of I star to be the left endpoints of each rectangle. Why? Because this thing is increasing, right? And so as this thing is increasing, the smallest rectangles are going to be the ones whose height is given by the left-hand endpoint. What about the largest possible Riemann sums? Well, the largest possible Riemann sums will come from looking at the choice where we make the right-hand endpoint. So, unfortunately, I'm going to have to erase this. Take a moment, pause this, make sure you sketch this down if you need to, but largest Riemann sum, this is going to come from the right endpoints. And again, not too difficult to see that this is going to be true, because if we look at the same kind of a picture, since this thing is increasing, the largest rectangles always take their height from their rightmost endpoint. And in a situation like this, where we have just an increasing function, that means there's only really two Riemann sums that I ever have to check, or at least two families, corresponding to the different numbers of rectangles. The one that has the left endpoints and the one that has the right endpoints. And if I can show that the one with the left endpoints and the one with the right endpoints both converge to the same number, well, then I can use the sandwich theorem for limits and say all of the Riemann sums have to converge to that number as well, because all the other Riemann sums are going to be sandwiched in between the smallest Riemann sum and the largest Riemann sum. So it seems initially, when you look at Riemann's definition, like it's just a truly horrific mess, where there's so many different choices involved that you'd never be able to get a handle on what is going on. But the truth is, for a lot of functions, you can get a pretty good handle on what's happening, because you just have to see what is the smallest option and what is the largest option. And if we can figure out what those two are, then all we got to do is study the smallest Riemann sum possible and the largest Riemann sum possible and show that they both converge to the same number, and then we're done. And in particular, this is going to be true as long as this function is a continuous function. It doesn't necessarily have to be continuous, but as long as it's continuous, then yeah, they will in fact converge to the same number. And the reason, roughly speaking, that they will converge to the same number is because as long as this thing is continuous, then the heights of the rectangles that you get with the left endpoint and the height with the right endpoint, well, since it's continuous, these two rectangles are approaching the same height. And therefore, the sums end up approaching the same number. And we can go through and we can make this argument rigorous if we want to. We can say that if a function is increasing and continuous, then the Riemann integral is well defined. So this is a theorem if f is continuous and increasing on a comma b, then the integral from a to b of f of x dx exists. In other words, all these Riemann sums have a well-defined limit and they all have the same well-defined limit. Therefore, the Riemann integral exists. And again, the proof here is not all that difficult to think about. So the proof is that we have the smallest Riemann sum, that's going to be the sum from I equals 1 up to n of f of x with the left endpoint times b minus a over n, and then we have the largest Riemann sum, which is the sum from I equals 1 up to n, f of x right endpoint star times b minus a over n. So we have the smallest and we have the largest. And then what we can do is we can think about what is the difference between these two. Well, the difference between these two is going to be the sum from I equals 1 up to n, f of xr star minus f of xl star times b minus a over n. However, what we know about continuity is that for any given epsilon, there is a delta, so that whenever I'm within delta of this point, then the difference between the function at the endpoints is going to be smaller than epsilon. I said that really poorly, but hopefully you get the idea of what I'm saying. Well, because of that, as long as n is large enough, these two are going to be close enough together to make this quantity as small as I want it to be. Therefore, this is going to approach 0 as n goes to infinity because of the continuity. Now, the continuity argument here is crucial. Without continuity, I can't say what these are going to be approaching. They could do some other crazy thing, but as long as it's continuous, then yeah, this is going to approach 0, and therefore we are going to get that this thing is well defined. Now, what about general functions? What if the function isn't necessarily increasing? Well, if it's decreasing, then we can make exactly the same argument, except we switch the function of the left endpoint and the right endpoint. Because if the function is decreasing instead of increasing, then the largest is taken from the left endpoints, the smallest is taken from the right endpoint. So that's all fine. What about if it's just continuous, but it's not necessarily always increasing or always decreasing? Well, if it's just continuous, then what we can do is we can break it apart into the pieces where it's increasing, the pieces where it's decreasing, and then we just have to worry about sort of what happens in a thin strip near the maximums and the minimums. But those thin strips approach having an area of 0. So essentially, it means that we can forget about what happens at those thin strips, and we can really just break up the problem into the increasing pieces and the decreasing pieces. And then we have that, in fact, since the Riemann integral is well defined for each of those pieces, since the limit exists for each piece, it exists for the whole thing. So I'm not going to go into the details of this. Again, this is sort of a bit of a quick review here. And honestly, it's not super important that you go through all of these details at the moment. But the fact of the matter is that the integral from a up to b of f of x dx exists when f is continuous on the interval from a to b. Now, I do want to emphasize that there are other situations where this integral can exist. It's not just when f is continuous. You can have functions with discontinuities, and yet the Riemann integral still exists. In fact, a lot of very interesting functions with discontinuities, the integral will still exist. But this is a guarantee that the function will exist under these circumstances, or the function. This is a guarantee that the Riemann integral will exist as long as f is continuous. And in fact, we can go further and say that if f is piecewise continuous, in other words, if f is continuous on this interval except for a few points where maybe it jumps around, then the Riemann integral is going to exist anyway. So that is a nice fact. Now, one of the things that we're going to do a lot during this semester is we're not necessarily going to have to compute Riemann integrals by hand. And this is a good thing, because computing the limit of Riemann sums is never an unpleasant experience for anybody. Nobody wants to compute the limit of a Riemann sum by hand, ever. Okay, it's a bad idea. You probably had to do it a little bit in a Calculus 1 or something. It's not something you want to do a lot of, okay? The good news is, and this is what we're going to cover next time, we have something called the fundamental theorem of calculus, which tells us you can compute this integral when it exists and when this function f has an antiderivative by using that antiderivative. In order to do that, we do need to talk about a few properties of the integral that we're going to make use of. So let me just kind of remind you of those properties, and also a little bit remind you, how do we understand that these properties are actually correct? How do we know that these properties hold true for the Riemann integral? So a few things that we can say about the Riemann integral. First of all, the integral from a up to b of a constant is equal to that constant times b minus a. How do you prove this with the Riemann integral? It's actually really straightforward, right? Because the thing is, the sum from I equals 1 up to n, the Riemann sum that I get is always going to be k times b minus a divided by n, but I'm adding that up from 1 to n, so that's just k times b minus a over n times n, it's always k times b minus a. In the limit as n goes to infinity, if I take the limit of something that is constant, it comes out to be the constant. So this simply approaches k times b minus a as n approaches infinity. So that is one important property of the Riemann sum. Another important property of the Riemann sum and its limit, and therefore the Riemann integral, is going to be the following. So, why am I writing a sum? The integral from a up to b of k times f of x dx is equal to k times the integral from a up to b f of x dx, provided that this exists. And how do you see this? Well, the Riemann sums here, this is the limit as n goes to infinity of sum from I equals 1 to n, k times f of xi star, b minus a over n. Well, that is going to be equal to, I can factor this k out of the sum. I'm allowed to do that because it's a finite sum and because of distributivity for arithmetic. So I factor that k out and I get limit as n goes to infinity, k times the sum, I equals 1 to n, sorry, I'm blocking the camera, f of xi star times b minus a over n. But now I can factor the k out of the limit, provided that this limit exists. And then I just have k times this integral, because now I just have k times the limit of the Riemann sums defining this Riemann integral. In a similar manner, that I'm not going to go through in detail here, but I will just kind of mention to you, because it's basically the same kind of argument, okay, but just very a small amount. If I have the integral from a to b, f of x plus g of x, this is the integral from a up to b, f of x dx plus the integral from a to b, g of x dx. How do you prove this one? Well, you do the same thing we just did, okay? You write down the Riemann sums. Now the Riemann sums are going to have an f of xi star plus g of xi star. But then you use the fact that addition is associative and commutative. And you split the stuff that has the f's in it and the stuff that has the g's in it apart. And you get one sum with the f's and one sum with the g's. Well, if the sums with the f's converge and the sums with the g's converge, in other words, if these exist, since the limits exist for each thing separately, the limits of them together exist, and it's just those separate limits added together. And therefore, we get this property from the Riemann sum. You do have to be a little bit careful, okay, because these don't have to exist in order for this to make sense. This could exist even though these two don't exist. An example of this would be, what if g of x is just negative f of x? Well, in that case, this is the integral of 0, and it doesn't matter whether these integrals are going to exist separately or not. We're just doing the integral of 0, which comes out to be 0 no matter what. So if these two exist, then this integral is also well defined, and it's equal to this sum. But maybe these two don't exist, but this one exists anyway. That's a possibility that we need to keep in mind. Fortunately, not one that we need to worry about too much, because mostly in this class, we're going to always be dealing with functions that are what are called integrable, where their Riemann integrals are well defined. However, not something, just as a general rule, keep in the back of your mind, this is not if and only if. If these exist, then this is true. But just because these don't exist doesn't mean we can say anything about this first integral. Now, using these properties and just these properties, oh, there's one more property that I need to therefore tell you that comes out as a result of these. So this property, well, two more properties. First of all, the integral from b up to a, f of x dx, is negative integral from a to b, f of x dx. Why is this true? Well, that's because the Riemann sums over here are the sum from 1 up to n, f of xi star, a minus b over n, whereas these Riemann sums are the sum from 1 up to n, f of xi star, b minus a over n. Notice that these are actually just negatives of each other. In other words, you get from one to the other by multiplying by -1. So if you interchange the endpoints in the Riemann sum, and you use the same definition, because why not use the same definition if you can, it just flips the sign of the integral. The other thing to notice is that the integral from a up to b of f of x dx is equal to the integral from a to c f of x dx plus the integral from c to b f of x dx. Why is this going to be the case? Well, the reason that we can say that this is going to be the case is essentially just those two theorems we just proved about how you can split something up over, you can split the integral over additions, and the thing about flipping the sign as you reverse things. So, for example, if a is less than c less than b, then all I have to do is I need to think about, say, f1 of x being equal to f of x when a is less than or equal to x less than or equal to c, and 0 when x is bigger than c. And then I can do the same kind of thing for f2 of x, and I can say f2 of x is equal to 0 when x is less than c, and it's equal to f of x for x greater than or equal to c. And then I can say the integral from a up to b of f of x is equal to the integral from a to b, f1 of x, sorry, I forgot my dx's here, plus the integral from a up to b, f2 of x dx. But if you split each of these integrals into the piece that happens when these are 0, so this one is 0 after we get past c, and this one is 0 until we hit c, then you can change these bounds to be a up to c and c up to b. And on those intervals, these are just f. So you are able to split things apart the way that I said. Now, I realize that my explanation there was very, very quick. Again, I'm hoping that you guys have sort of seen some of this stuff before, so you're familiar with these properties. And yeah, so the point is that we can split up the Riemann integral in all these different ways. The reason we need to know this is because it's going to allow us to prove that the fundamental theorem of calculus is true for the Riemann integral. And that's what we're going to do next time. So I'm going to leave things off here. Oh, and I should say something about the uploading schedule. So my goal here is to have all your videos for the week uploaded by Thursdays, usually. So I'll probably upload 2 or 3 videos a week, just depending upon what topics are coming. Sometimes I may do more. I may split things up a bit more, but we'll see. And I'll try to get those videos uploaded on Monday, Tuesday, Wednesday, and Thursday. But do keep checking back on Blackboard just to see if there's any new videos or anything. I would like to be more organized than this, but we kind of made this an online course at the last minute, so I didn't have a lot of stuff prepared to go fully online directly. And so, yeah, just keep checking Blackboard because I'll be uploading things throughout the week. All right, so I know today was probably kind of a hectic very quick refresher of this stuff for you, but we will continue going over the stuff in Chapter 5 of your textbook and reviewing it throughout the rest of this week. So do let me know if you have any questions, and good luck. I will talk to you again soon.